Now, in learning to name quadrant 2 compounds polyatomic non-acids, it will become readily apparent why you had to learn the entire family name. Because it is the anion piece that is used in the quadrant 2 name. The acids themselves make up the quadrant 3 name, but it is the anion of those acids which goes into making up quadrant 2 names. As a quick aside, note that we've only dealt with 3 types of polyatomic acids, those that have only one acidic hydrogen, in which case the anion becomes a -1, those with 2, the anion becomes -2, and those with 3 acidic protons, in which case the anion is necessarily going to become -3. Examples of those include nitric acid, sulfuric acid has 2, and phosphoric acid has 3 protons. Now, why the charge on the anion is important, of course, is because that's the charge which must be neutralized by some positive piece to make a charge-neutral molecule. Let's work through an example step by step. Identify the 2 pieces, and we name this sodium. You recognize the metal as the positive piece. And the last one is phosphite. Now that's different. It's not sodium phosphorotrioxide. What you must do with quadrant 2 is to recognize the PO3 as being the anion from a polyatomic acid. The key to naming polyatomic non-acids is to recognize that the polyatomic ions, you're going to treat them as a single unit. So once you recognize the polyatomic anions, you just named it as a type 1 and looked at the metal and saw it was a type 1, sodium, and you stopped. Well, let's work another one. Here we see that we have 2 pieces. We have iron, and the second piece is a PO4 group. We recognize that as a phosphate group, as being a member of the phosphoric acid family. And so we have iron phosphate. So we've named it as a type 1, and we check. Yep, there's a metal. Is it a type 1? No, it's not, so we're going to name it as a type 2. So what do we need now? A Roman numeral. That means we have to know the charges. We are looking for the charge on the iron. We know phosphate has a 3-, and we have 2 of them. 2 times -3 is -6. What -6 will equal to 0? That's got to be +6. And 3 times what equals 6? 3 times 2. Therefore, this material is iron 2 phosphate. Let's work a couple of more, but this time instead of going from formula to name, we'll go from name to formula. Taking the first compound, I see the 2 pieces. I see this compound is made from a sodium ion and a phosphite anion. Now, what was phosphite again? Oh, that's right. It was a member of the phosphoric acid family, and it bears a charge of -3. Is this compound charge neutral? Let's see. What's the total negative charge? This is a very important point I'm going to make here. The -3 applies to the PO3 as a single unit. Remember, treat polyatomic anions as monolithic or single units. So the entire PO3 has a -3. But how many PO3 groups do we have? Only 1. So my total minus charge is -3. But my total positive charge right now is only a single +1. So this is not a charge neutral compound. How can I get it to be charge neutral? Easy. I see that I can use the cross multiply trick. And in cleaning this formula up, gives us Na₃PO₃. One more. I see the two pieces. I have an iron. Do I know the charge of this iron? Actually, even though it's a type 2 metal, I do, because that has been declared as a +2. And what was phosphate? That was also from the phosphoric acid family, and it bears a charge of 3-. Is this charge neutral? In my mind's eye, I'm going to make sure that I treat the PO4 as a monolithic unit. And I see my total negative charge is -3 and my total positive charge is +2. It is not charge neutral, but it can easily be made so by cross multiplying. Because there's more than one unit, only now do I use parentheses to differentiate it. And so cleaning the formula up, it's Fe₃PO₃, 2, iron, 2, phosphate. As a procedural thing, remember, if you have only a subscript of 1, you do not draw the parentheses. Don't do that. You only use parentheses if there's 2 or more of the polyatomic unit. In the case you didn't notice it, the two formulas we just derived are the same two formulas we named in the previous exercise. So you now have the knowledge to name quadrant 2 compounds in going from formula to name and name to formula. So remember, don't make naming quadrant 2 names any harder than you have to. Just treat the anions from the polyatomic acids as a single unit, and then use your quadrant 1 rules that you already know how to use.